You've probably noticed as we've been going through the isoquant and isocost curves that it looks really similar to the consumer choice problem where we have our indifference curves and our budget constraint. And the math here, again, is the same, but the intuition is really different because in this example, what we're trying to do is to choose the labor and capital that would minimize our cost given a certain target for production. And so here we're doing a minimization problem rather than a maximization problem. And the way that we can conceptualize this is that we want to hold production constant. So we have some target level of production. And that is represented here by our isoquant, right? This is our target level of production. Now, there are lots of different combinations of labor and capital that could be used to reach this level of production, which you can see is given by the isoquant that we've drawn here. But each of those combinations of labor and capital will have a different cost. So you can see point A, point B, and point C are located along different isocost curves. What we would like to do is to produce this level of output at the minimum possible cost. And so we want to be on the isocost curve that is lowest while still intersecting our isoquant. So here we are on the lowest isocost curve that intersects or touches the desired isoquant. So this combination of labor and capital found at point C is the optimal or cost minimizing combination of our inputs. So how do we find that point mathematically? We need to compare our slopes for isocost and isoquant curves, right? At the point of tangency, the slope of these two curves will be the same. And we will do that by writing out our minimization problem using the Lagrangian method, just like we have done before. So here, notice though that what we're trying to minimize is our total cost. So we are shifting the total cost curve in until we reach the tangency. And this is unlike before where we sort of held constant our budget constraint and then shifted the indifference curves out until the tangency was obtained. All right, so here we're minimizing total cost subject to the target level of production. And so we can write that out generically as, right, minimum choosing labor and capital of our total cost function plus lambda times, now we want to rearrange this constraint so that it's equal to 0. So we would have our target level of production minus some function of labor and capital that describes production process. And then when we take our derivatives with respect to labor, we would get W minus the derivative of our production function with respect to labor times lambda. And then we would set that equal to 0. We take the derivative with respect to capital. I would get R minus the derivative of the production function with respect to capital. And of course, I would set that equal to 0. And then combining these, and I can combine by dividing here, I get W over R is equal to, and then on the other side, I've got, this is really the marginal product of labor and the marginal product of capital. So I've got the marginal product of labor over the marginal product of capital. And this gives me the optimality condition for my cost minimization problem, or in other words, the optimal, this will yield the optimal capital labor ratio. And you notice that what we've done here really is to set the slopes of our two curves equal to each other. Remember, the slope of the ISO cost curve is the ratio of prices of the inputs, and the slope of our ISO quant is the marginal technical rate of substitution. So again, what we're doing is finding this tangency that tells us the quantity of labor and capital that we can use to produce our target production level that will minimize the cost of production.